In this video, I'm going to show you one of the most important concepts for controlling EMI and PCB design, so you can pass EMC tests faster and with fewer surprises and less money wasted. My name is Dario Presu. I'm fourth generation electrical specialist and principal EMI control engineer at presuelectronics.com, where we train engineers including 400 to 500 subsidiaries to master EMC design with a strong focus on practical EMI control. One of the most important concepts in designing printed circuit boards for low electromagnetic interference, or simply EMI, is understanding electromagnetic fields, specifically how to contain and control them. EMI is fundamentally about field containment, and it's about controlling where these fields need to be strong and where they need to be weakened. And when we discuss fields, we are referring to both electric and magnetic fields. Therefore, if our goal is to design PCBs with low EMI, we must understand how these fields behave and how we can control them. And once we master this understanding, we can then achieve a high-performing circuit that passes electromagnetic compatibility, or EMC, tests, which are an essential requirement before any product can be sold in the market. So one of the most effective approaches to understanding electromagnetic fields is to visualize them. And while this phenomenon can be complex, we can have some simplified representation to help us grasp the fundamentals that are essential when designing or debugging products for low EMI. And the first visualization that we need to understand shows us how fields surround a single conductor. So this is the basis for understanding EMI. How one single conductor, this is important because later on we're going to see the dynamics when we introduce also the return conductor. And so in this scenario where we have the single conductor, the circle at the center represents a conductor viewed in the cross-section. And so surrounding this conductor, then we have the magnetic and the electric fields, which are together form the electromagnetic fields. And so the magnetic field is quantified by the number of lines of magnetic force, which are denoted by the symbol phi. And then these magnetic lines encircle the conductor and they are forming a closed loop that represents the magnetic flux generated by the current flowing through the conductor. Then we have the electric field, which is represented by the dashed line in the diagram. And these lines originate from the conductor and are measured by the number of lines of electric force. They are denoted by this symbol psi. In the case of a single conductor, these electric lines then radiate outward as straight lines from the conductor. Now, once we introduce the return conductor, the behavior of the field changes and dramatically. So in these two conductor scenario, then we have the magnetic field lines that become concentrated between the two conductors, forming stronger, more focused loop in the space between them. Outside of this space, the magnetic field lines spread out more broadly. For the electric field lines, they change also their behavior significantly, and instead of radiating outward from a single conductor, then the electric field lines now start from one conductor and terminate at the other. Now, what is the key takeaway from this visualization? The magnetic field lines always form closed loops, while the electric field lines, they terminate at conductors. And so this distinction leads us to describe the magnetic field as a magnetic circuit where the field lines loop continuously, and the electric field as an electric circuit where the field lines originate and terminate at specific points. Now let's see this in a different perspective when we have the polarities and how they interact. So when conductors have the opposite polarities, electric field lines originate from one polarity and terminate on the opposite polarity. And so this demonstrates how fields interact within the positive and the negative conductors, with the lines of force creating a direct path between them. Conversely, when two conductors have the same polarity, the fields repel each other. And the electric field lines then push away from each other, illustrating how the polarities repel and how this affects the distribution of the electric fields. Now, why is this important for applications like printed circuit board? So let's have a look at a printed circuit board. So this is the representation of a printed circuit board. And so in here we have the signal layer, which is shown in red, containing the signal traces, and then the return reference plane, which is depicted in blue. The stack up in here refers to the specific arrangement of the PCB layer, so including the conductive copper layers, where the signal traces and the reference plane are located, as well as the insulating layer and pre-preg or the core material that separate and support these two conductive layers. Now, the dielectric layer is actually really important, and I would say it's also more important than the conductors themselves, because the conductors themselves, they are there to guide the fields. Where the fields actually propagate is in the dielectric. So also this is important because when we have to picture how the signal propagates through the printed circuit boards, we have to picture the electromagnetic energy propagating through the dielectric and not in the conductors. So when we observe these fields in the PCB configuration now, the behavior is similar to the two conductors which were shown before. But what does it change in here? Instead of having the two conductors like we had before, we rotate them to 90 degrees angle. And so this comparison here is one of the foundations that we need to understand when we want to design printed circuit boards with low EMI. Because what we effectively are doing in here is trying to channel these fields. So with the conductors, we are essentially designing the river banks that contain these fields. So picture it like a river in between the river banks. We're trying to do essentially something similar because we are trying to channel these fields and to contain them in between these two river banks, which are the conductors. Usually when we have EMI issues, this is one of the issues that we have, that we didn't design the conductors to contain the fields, but we designed them with the electron flowing through the copper in mind. So in practical terms, the fields in here of the signal trace in a PCB are significantly influenced by this return reference plane, because the fields not only terminate at the surface of the return plane, but also they tend to bend towards it from the opposite side. And so this bending effect helps contain the fields and prevent them from spreading outward as they would in the absence of the return reference plane. And so this return and reference plane, like I was saying, acts as a boundary that contains the fields, preventing them from dispersing freely into the surrounding space. And this is why it's important, because without this plane, the fields will continue spreading from the signal trace, as in the picture of the signal conductor. So understanding how these fields are contained by the return reference plane is then essential for us in printed circuit board design, because the choice of the stack up, so how the layers of the board are arranged, then they must be based on this principle. And so here the key takeaway is this one. If we remove the return reference plane, we allow the field to expand uncontrollably. And this is one of the major reasons why the PCB often fail EMC tests and generate EMI issues, because the signal traces without an adjacent return reference plane, they lack the necessary containment for the fields, leading them to excessive radiations. Because essentially, when we measure the fields during the EMC test, we often find that the level exceeds these requirements, because without a return reference plane, the PCB effectively becomes a radiator, and then it emits unwanted electromagnetic energy. And so in real-world application, what does this mean for us? In practical scenarios, particularly with common electronic consumer products, if a printed circuit board lacks a return reference plane adjacent to the signal trace, then the earth ground will act as this return path. And this causes the fields to continue expanding until they eventually reach the earth ground or other nearby conductive structures, because essentially the earth ground becomes a larger conductor. And so this is the reason why the expansions can lead to the formation of common mode currents, which, by the way, are highly effective at radiating electromagnetic energy. And so these currents then can easily cause a product to fail EMC test if the radiated fields exceed these acceptable limits by the standards. And so to mitigate these EMI issues, the first and most important rule of thumb in PCB design is for each signal layer, there must be a return reference plane adjacent to it. And this return plane should be free of discontinuities, such as large holes, gaps, cuts, or any other malformation that could compromise its effectiveness. So the return reference plane should be as integral and as close as possible to the signal trace. So this approach for me has been one of the key to successfully passing EMC test on the first attempt. Because by properly designing with an adjacent continuous return reference plane, we ensure that the fields are then effectively contained, which then reduce the chances of EMI issues. So now I want to also show you this picture here, because this is the model that we have been taught when learning electrical circuit design or electronics. And so this modeling here is where we have the source of the energy, or in this case, the source of electricity in here. Then we have the load, and then we have the return conductor. So these will be what we usually call ground, and then we have the positive conductor, or what is called the signal conductor. And so you can see that in this model here, we have the source, then we have the electrons, the flows inside the conductor. So the signal conductor is the one on the top in here. Once they reach the load, they go back. And in here you see there is a little switch that allows us to control this flow of electrons or flow of electricity inside the conductor. So this is the wrong model that we have been taught. Now, I propose you another simple model, but this time in terms of fields instead of in terms of our electrons. And so in here, instead, we have the source over electromagnetic fields or electromagnetic energy. Then we have the top conductor, which is this one red on the top. We have the return conductor here, which is the black one. And then we have the electromagnetic energy or electromagnetic fields. So you can see in here how it changes the perspective, because in the first model, the fields or the electrons were inside the conductor. In this model here, instead, the fields are in between the two conductors. So this is why the analogy of the river banks makes more sense, because we are containing the fields in between these two conductors and not inside one single conductor and then channel it through the return conductor. In the model on the right hand side, what we are doing is creating the conductor structures so that we can contain the fields in such a way that they don't escape from this conductor structure. And so you can see that then the fields are propagating in between the conductors, so in the dielectric, and then reach the switch. And then in here, I can control the energy, and then it reaches the load. And now the circuit here is still closed, because in here we have the signal forward current on the signal conductor and the return current on the return and the reference conductor. And so this will still be a loop because of the way the current will be established on the surface levels of the conductor. And now the other image I wanted to show you here is this one when we have then the wires. So what happens when we have the wires? You can see that in here the S denotes the Poynting vector. So the Poynting vector is propagating in this direction. Then we have the electric field, which is these red arrows that starts from the red conductor and terminate on this black conductor. So one is the signal conductor, the other one is the return and reference conductor. Now here it makes a little bit more sense of why we call it also return and reference. The reference in here is because we are providing the reference to the signal conductor. So you can see also here on the left-hand side, we're providing the reference for the electric fields to be established in here, because the electric field, they start here on the red conductor and they terminate in the black conductor. And so the magnetic fields instead, they are around the conductor. So they're surrounding the conductor, forming circles. So if we look at the cross-section view, here we can see clearly how the circles are surrounding each conductor. So we have these two conductors and they are surrounded by these circles here. And then also we can see here how the electric field starts from one conductor and they terminate on the other conductor. And this is what allows the signal propagation, which is essentially the electromagnetic energy propagating here, which is also denoted here by the Poynting vector. Now try to picture this in a printed circuit board setup. When we change the structure of the conductor, we're essentially making these two rounded conductor flat. Still, we have the same approach of field containment. We want to contain this field as much as possible in between these two conductors, which is essentially where the signal will propagate. Now, how does this apply also to printed circuit boards in reality? So let's take a look also at a simulation for a printed circuit board where we have a trace of the printed circuit boards, and we can see in here we have a signal that changes the polarity. So we can see that electric fields, they first propagate outward and then they propagate inward. But we have the signal trace here on the top, and then this one on the bottom there, where the fields then they reference to is the return reference plane. Then we have also the magnetic field. So you can see how the magnetic fields encircle this signal layer conductor, first on one direction and then on the other direction as the polarity of the signal changes. And so this simulation is to help you visualize the picture in here, which shows you what happens when the signal is propagating through the printed circuit board. So you can see that the fields are not inside the conductor. This is what's really important, because when we're designing the printed circuit board, we need to build the structure that contains the fields. So we cannot use a single conductor. So this is why it's important, because when we're designing two layers printed circuit board, where both layers are used for signals without a return reference plane, then you can already picture how these fields will spread out from both the signal layers, which then becomes a problem, because now the fields from both the signal layers are compromising each other, essentially. They are contaminating each other. And then if I measure this with the EMC instruments, so if I go, for example, to do a radiated emission test, I will pick up these fields because I allow them to grow large, and now they are above the limits of the standards that I need to comply with. So I hope you enjoyed this video here, and if you have some questions or if you would like to dive deeper into these topics, then you can check the link in the description and you can join the academy where we can help you become a PCB design and EMI control specialist. Bye bye.